Hello, everyone. So we're going to get into, we've got 3.2 today. We are on page 66 in your student journal. So again, just as always, if you need to pause the video, whatever you need to get the vocab down. If you want to give yourself a title for 3.2, we're talking about linear functions. Okay, so make sure that you've either watched the video or you remember what we talked about yesterday in 3.1. All right, we were talking about functions in general. Okay, how can you tell if something is a function or not a function? Now we're getting a little bit more specific than even that. We're talking about, okay, how can we tell if something is a linear function? Okay, so just like it sounds, when we say a linear equation or a linear function, we're talking about something that we can graph as a line. Let me draw that box better. Okay, linear means line. Okay, so we've got a couple different things we're talking about. So we have a linear equation and two variables. This is anything that we can write in this y equals mx plus b. Okay, we're going to get way more into this as we go throughout this chapter. Okay, remember that is what we call slope-intercept form. Okay, so m and b will be some constants, will be some number. Okay, so you might see y equals 2x plus 3 or any combination for m and b. Okay, so kind of the trick when you're looking at different equations, there's a part of your homework where it's going to ask you, is this a linear equation or not? The key is the y and the x, they shouldn't have exponents. Okay, if you have something squared, that's an alarm bell. That's not going to be linear. Okay, if you have, let's say, like the square root of y or of x, that's not going to be linear. Okay? If at any point in your equation you have something like 2xy, if you're multiplying those two variables together, that's not going to be linear. Okay? The way to tell that something is a linear equation or can be expressed as a linear function is if you have the y and the x in two separate terms and they don't have exponents. Right? Then it goes into linear function. So linear equation, linear function, for now they're pretty much the same thing. Okay, we'll get into on 3.3, we'll get into that function notation and the difference between expressing something as a function and an equation, but for now it's really the same thing. Okay, so it's when we have a function whose graph is a non-vertical line. Okay, so anything that we can put on our xy plane, that's a line. Okay, that's a linear function. The thing to watch out for, I say a non-vertical line. Let me draw another coordinate plane here. Okay, let's say I just had, let's say that's my x and this is my y. Let's say I had this line. Okay, and I asked, okay, is this a linear function? That line, that graph, doesn't pass, remember, our vertical line test? Okay, if we have a vertical line, it's going to hit every single point on this graph. Okay, so vertical lines are not functions. Okay, it's just one of those kind of tricky little rules that you need to remember. A horizontal line is fine, okay, because that's going to pass the vertical line test. Any other straight line is going to pass, right? It's just vertical lines because they don't pass that vertical line test. Okay, and then a nonlinear function, right, is going to be a function whose graph is not a line at all. Okay, so that's going to be what you're trying to tell. Okay, yesterday you were trying to tell, okay, is this a function or not a function? Now we're generally going to give you functions, and you're going to have to decide, is it linear or nonlinear? So you might have a parabola. All right, you may have something that looks like this, okay, where you've got a curved part of your line, right? Anything that's not just a straight line, that's a non-linear function. Okay, and the last one over here, the last one that I really care that you do at least, the solution of a linear equation in two variables. That's a lot of words to basically just say any coordinate that's a solution to an equation. Okay, so we'll get more into this again as we start graphing these equations, but any coordinate, let's say I gave you y equals 3x plus 5. Okay, so then that would be any coordinate that's a solution to that equation. Okay, that's what I mean by a solution of this linear equation. Anytime we talk about in two variables, it's because I've got a x and a y. That's what I mean by two variables. Right? This discrete domain, continuous domain, I really don't care about those specific terms. All right, in case you are curious, discrete is when you have like those graphs we've seen of just the individual points, versus continuous is when we have a connected line, but I'm not too worried about that. All right, so we're trying to figure out if different functions are going to be linear functions. And just like yesterday with 3.1, there's a whole bunch of different ways that we can express these different functions. Okay, and I might ask in each type of this, probably not in words, I don't think, okay, an output is 3 more than the input, but I could definitely give you an equation like this. Okay, an output y is the input plus 3. Okay, this is the same thing. Okay, so I could ask you, all right, is this going to be a linear equation or a linear function? All right, remember that rule. I don't have any exponents. Okay, x is not squared, y is not squared, nothing's the square root. I don't have x times y, they're all separate terms. All of those things tell me this is a linear function. All right, sometimes I'm going to see this, all of that information put into a table like this, input and output. Okay, that makes sense, right? If we go back to the little function machine deal, the function is this y equals x plus 3. Okay, so my input is my x. I'm plugging in -1. So y equals -1 plus 3. That means y equals 2. And my output is 2. Okay, that's where these numbers are coming from. I'm not going to do that with every number. I just wanted you to see what these numbers are that we have here in this table. So the way you can look at a table and decide, is this a linear function or not, is go from input to input to input and go, okay, how did I get from -1 to 0? Well, I added 1. And from 0 to 1, I added 1. And I added 1. Okay, it's a constant rate of change here on the input. In order for it to be linear, it has to be constant for the input and the output. Okay, it doesn't have to be 1 over here. It can be a different value, but as long as it's the same for every input and for every output. So from 2 to 3, I add 1. 3 to 4, same, I add 1. And 4 to 5, I add 1. We have a constant rate of change. Okay, so rate of change is as my x changes, my y is also changing. Okay, so we know that these are changing at the same rate. So this is a linear function. Okay, very similar. Remember these little diagrams like we did yesterday? It would be the same process. From each input, you would go, okay, I'm adding 1, I'm adding 1, I'm adding 1. Okay, same thing over here. Okay, we know this is a function because we have the same rate of change. And let me not be confusing here. It doesn't have to be the same for input and output. If I had one, for example, that went up by 1 for the input and then up by 4 for the output, or maybe subtracted by 3 for the output, that would also be a linear function. Okay? As long as all the inputs are the same and all the outputs are the same, it is a linear function. Let me go ahead and get rid of those negative 3's. Obviously, we didn't subtract 3. I just wanted to show you it doesn't have to be the same on both sides. Okay, and the same thing over here with the graph. The graphs are a little bit easier because for most people it's kind of simple to look. All right, and you can see this is a straight line, so it's a linear function. But sometimes you might have one that looks a little bit tricky. The way to tell them this is the same thing, okay? From this point to this point, I went up 1 and over 1. Okay, from here to here, I went up 1 and over 1 and up 1 and over 1. From this point to this point to this point, it's the same rate of change. Okay, so we have a linear function. Right? And like I mentioned before, I don't really care about this discrete and continuous domain. Again, if you just want to know for your own information, discrete is when you've got these individual points, and continuous are when you have these numbers all connected. But we don't have to spend too much time on that. All right, so it's giving us these graphs, and we have to decide, is this a linear or a non-linear function? Okay, so this first graph right here is a great example of something that it looks like it's pretty close to being linear. But if we actually look at point to point to point, if we look at this point and then this point, okay, I go up 1 and over 1. Okay, let's look at the next point on our graph. Okay, this is the next point that's right on an even number. We go up 1 and over 3. Okay, that's not a continuous rate of change, so this is not a linear function. Okay, let's try this one. Okay, this looks like a straight line, but let's look at what that actually means in terms of the different points on our graph. Okay, it intersects over here. Okay, the next point is this one right here at the origin. Okay, we go up 1 and over 1, 2, 3, 4. Next point is right here. We go up 1 and over 1, 2, 3, 4. We've got a constant rate of change. So this one is a linear function. Right? Now again, we have the same information. We have this function, but now it's not in a graph, it's in a table. So let's look and see if we can decide. So it says x and y. So first I'm going to look at my different x values. So how do I go from 1 to 2? I'm adding 1. I'm adding 1 from 2 to 3. And I'm adding 1 from 3 to 4. Okay, it's constant there for my inputs. Let's see if it's constant for my outputs. Okay, from -1 to 2, I'm adding 3. From 2 to 5, I'm adding 3. And from 5 to 8, I'm adding 3. We've got the same rate of change here through my x's and my y's. All right, so this is a linear function. Again, it doesn't have to be the same number. I've got a 1 for my input and a 3 for my output, but as long as my inputs are all the same and my outputs are all the same, you've got a linear function. Okay, and for number 4, let's try this out. Okay, -1 to 0, that's adding 1. Usually they're going to be adding 1 for your input. Adding 1 and adding 1. Okay, from 0 to -1, I subtracted 1. Okay, -1 to 0, I'm adding 1. 0 to 3, I'm adding 3. I don't have a constant rate of change here, so I have a non-linear. How do I spell linear? Non-linear function. All right, and here we have some examples, or we're trying to figure it out just from an equation. All right. If you really wanted to, you could plug a bunch of numbers in for x, see what you get for y, see if it works in the table. That's way too much work. All right. Instead, what we need to do is we need to try and figure out, just from looking at our equation, if this is going to be linear or nonlinear. So we've got this y equals 3 minus 2x. Y and x, neither of them have exponents. Neither of them are in a little square root sign or anything like that. Okay, x and y are separate terms. We're not multiplying them together in one term. So this to me tells me this is a linear function. Okay, and over here for number 6, y is equal to -3/4 x cubed. That exponent tells me right away that should be an alarm. That is a non-linear function. Right? When you get those exponents, you get graphs that look curved, not just a straight line. Okay, I'm not too worried about the discrete continuous stuff. All right, and then tomorrow we're going to get into function notation. All right, go ahead and get started with this assignment, and I will see you guys tomorrow.